working. All right. So lab 12 is going to be on ARP spoofing and man in the middle. It's a pretty common network attack. And in this lab environment, it works pretty slick. In another class in my undergrad cybersecurity cyber ops course, we've been talking about man in the middle today. And this is the one that you would do, like, say you were sitting at a hotel and you wanted to capture all the wireless traffic, reroute it through you, and then send the traffic back out through the rest of the hotel network. This way you could capture all the client data that's out there on that network. This is one way that you could go about doing that. So. See here, pause for just a second. All right. So again, this one's going to deal with ARP spoofing, which is one way that you can go about doing a man in the middle style of attack. We're going to use EtherCap in order to do this man in the middle. There's tons of different ways to do it, but this one's fairly straightforward and easy. So getting that going over here, we're going to go ahead and pop over to Kali. This is a fairly short lab, but we can kind of explore with it. Hit the right button here. Okay. Get logged in. Now, the first thing we want to do in this lab is disable Ethernet 0. Remember that Kali Linux has 2 Ethernet ports coming out of it. We specifically want to disable ourselves going out this direction. We want to use as if we're on the local network. So clearly this attack won't work outside the firewall and outside the network. We need to act like we're on the LAN. So to do that, come over here to the Ethernet, and we'll go ahead and disconnect our Ethernet 0. And then we'll go ahead and click on Ethernet 1. And this should put you on the IP address of 192.168.0.2. So we're turning on this link here. So that all should be good. We can come in here and do an IP add and see for sure that we're on the right network, which we can see is up and running here. And if we wanted, we could go ahead and do a ping just to make sure things are working. So in this topology, we know the default gateway is 254. And we can see our default gateways up and running. Okay, so again, what we're going to use is EtherCap, which is a graphical tool that allows us to use the EtherCap program. -G just means we're firing it up for the graphical side. And then in this primary interface, we want to make sure we're going out Ethernet 1. That's the one that we just turned on. And there's a couple of things that we want to double check here. So what we want to do is click this check mark up here, which will accept those changes that we had turned on. And we can look to see that it starts sniffing traffic on the network. Okay. But in order for us to target something, we need to tell it which MAC address we want to spoof. So if we click over here on this magnifying glass, it's going to scan our network to see what other traffic and hosts that we may see out there. Once we click on that, we'll see that it detected there's 2 other hosts on this network. If we look at the topology, we should see OpenSUSE and we should see our firewall. Okay. So if we click over here and on the host, which is this one just to the right of the magnifying glass, we can see those 2 IP addresses there and to the MAC addresses that they're associated with. So in this case, we want to click on .30, which we are going to look at the topology. That's OpenSUSE. This is going to be our target of the man in the middle attack. So what our plan is right now, OpenSUSE would send traffic out the firewall and on out to the internet. What we wanted to do is anything that's destined for .30 to get sent to Kali, then reroute that traffic back through the pfSense firewall, thus putting ourselves in the middle of this network. So we click on .30, we're going to click to add to target 1. And then we click on the firewall and say add to target 2. That's what we're going to be blocking our traffic and sending our traffic back out towards. All right, so now we can sniff traffic, but we haven't actually taken over ARP at this point. So if we actually saw traffic, for example, we click on OpenSUSE, we go ahead and log in. And then we're going to simulate going out to the OWASP, which is going to be like our internet, right? So that it has to go through the firewall and out to someplace else. So if we come out to OpenSUSE and we go out to the OWASP box, you can see we pull up that page. We go back to our Kali box. Right now, we don't see that traffic going through there, but it is actually sniffing that traffic as it goes through. Now, to be our man in the middle side, we have to poison that ARP. So we're going to click on this man in the middle menu and then do some ARP poisoning. To do that, we're actually going to click on the man in the middle icon, which is what we have here, and we'll do ARP poisoning. This is currently running. We want to leave these default options here and click OK. Now, if we look at our output down below here, you can see that we have group 1, meaning that that's where we're bringing in traffic. We're going to be sending it out to this interface here. So just like I did before, we go back to OpenSUSE. And what we want to do is act like we're going to the firewall. So we're going to pull up the OS or the pfSense box here. And we can see we get this login screen here, right? We type admin to log in, and in this case, it's pfSense. We hit OK. If we go back to Kali, we can see that we captured the traffic of us going to that particular website. But if we look inside the sequence down here, we'll actually see that we're able to capture the username and password. And the reason we can do that is we're actually sending that traffic from OpenSUSE. It thinks that we are trying to go to pfSense. So what we did was we set the MAC address of the Kali Linux box to the same MAC address that's on here. And we told pfSense in order to get back to OpenSUSE, we actually set the MAC address on our Kali to that so that the traffic goes here and then back out to OpenSUSE. Essentially routing all that traffic through Kali before it gets back to OpenSUSE. And we can see on this case, because it's plain HTTP traffic, we can capture usernames and passwords and anything else that we see on the traffic wise. But there's a lot more fun things that we can do besides just capturing usernames and passwords. So if we click on OpenSUSE at the top and we go out to our OWASP box, we can take a look and we can see all of our graphics, right? We got this little icon up here and we got these little plus sign icons on everything else. And you get a little image down here as well. What we're going to do is change all images from there on out that goes through that traffic. So if we click on our Kali Linux box, which, by the way, we're going to go ahead and close our session here. Okay. Back on Kali, we're going to enable a filter. So to do that, we have to click on what looks like the file browsing icon. That's not my filter. That's the sniffing. I got to remember where I put this stuff. I'm the one that wrote this lab. Been a little while. Let's see. Click on the file browser icon. That's a really horrible description. Filters, load a filter. Okay. Now in this case, there's some pre-written filters that are inside of here. You guys will actually write a little bit of your own. But for now, what we want to do is go to home, in this case, root. And inside root, we want to take a look at our filters. And we have a couple different filters here, and we're going to look a little bit more at that. I'm sorry. So before we do this inside of EtherCap, we're actually going to take a look at what that filter looks like. It's the reason I missed it. So forgive me. We're going to do this. We're going to go to filters, and we're going to go to our logo filter here. And we're just going to take a look at the raw code before it's compiled into a filter. So what this particular one is going to do is it's got an if statement, and we're going to make sure that we are looking specifically for TCP traffic. We're also going to be looking for traffic destined to port 80. We're going to specifically look through the data that comes through and look for accept encoding, and we're going to replace accept encoding with accept rubbish. And then our message is zapped accept encoding so that we can see this out on our main screen. What we're also going to see is if we look for port TCP and 80 traffic, we're going to look through the code, in this case, the HTML, and any place that we see image source, we're going to source it with our own logo that we have out here on our system. If it's all caps, we're also going to go ahead and replace it with this one here. So we're going to tear through the HTML as it's passing through our machine, look for this particular line of code in any HTML, and replace it with one of our own. If we want to know what that image should look like, we can come back here to the folder. Notice that we are hosting this on our own little web server, right? So to do that, we have to come over here and look at where our web server would be hosting traffic, which is in our slash. In our root folder, we'll go to var, www, HTML. We can see this logo. And if we open this logo, this is the image that we plan to replace everything with. Now, obviously, this isn't over the top, but we could replace this with whatever we wanted it to be. So if we go back to our code, and you can see in here, again, what we're going to do is send a message to the main console here and say that images have been replaced, and we're going to zap any encoding that comes through here. All right, so to get this started, we have to start our web server. And then to start our web server, we need to go ahead and start a extra terminal. And we're going to run service Apache 2 start. And that is going to start our web service. If we want to make sure it's up and running, we can do service Apache 2 status. We can see that it's now currently up and running. We actually went to our own page, go a little off script here, open up a web browser. We go to ourselves. We can see that we have the Apache default. And if we go to the logo.jpg, if I spelled that correctly, it's just JPG. There we go. And we can see we're hosting up our image file that we wanted to have here. Okay, so now we've got that all up and running. We're going to go back to EtherCap, and we're going to go ahead and click on the three dots, go to filters and load a filter. And what we're going to look for here in load a filter, if we go to our home, filters, and our logo EF. EF is just the compiled version of that filter that we looked at before. So I'm going to click on that one and hit OK. We'll notice down here that it has loaded our content filter down below. All right, so now that that's up and running, let's go to OpenSUSE. We'll go back to this website. And we're going to go out to our OWASP box again. And notice that we've replaced every image on the website with whatever image we wanted to have in there. So not only are we capturing logins and traffic, but we can completely rewrite the HTML on the fly when that traffic comes in there, just by simply hosting it up from ourselves. Now, normally a hacker wouldn't try to necessarily expose themselves in this case, but what we're going to do is just, instead of just intercepting pictures and writing our own pictures in, we're actually going to throw up our own Java alerts right into the traffic. Remember that this is unlike the browser hack that we were doing in those skills. So like when we did the man in the middle, so to speak, with the browser hack, we could pull in all their traffic, see what was in there. This one, we're just going straight raw with EtherCap and doing ARP poisoning. So to do this, we're going to go back to Kali. Take a look at our folder again. And let's go back out to our filters. And this time we're going to take a look at this one called Hacked Alert. Notice that it still does the if sequence, and it's particularly looking to zap and say that we've accepted encoding. Inside this last section here, what we're going to do is search through all of our data and look for the head section. And inside that head section, we're going to throw in a JavaScript flag in there. Now, in this case, it just says you got hacked. And then we're going to send a message back to our main filter that the filter ran, is all we're going to say. Now, we could clearly dump in our own JavaScript code that would do all sorts of things in here that would run at the moment that page got launched. In this case, we're just going to pop up a simple alert. So back over here in EtherCap, we're going to launch that filter. Notice all the images that got replaced when they got replaced. And we can see zap the accept encoding. We can change that message to whatever we wanted. Yeah. So in this filter, we're going to go ahead and load a filter. Go back out to home, filters, and then on the hacked alert, we're going to make sure we get the EF. There we go. And so now we've launched both of these that are inside of there. So now if we go back to OWASP or OpenSUSE, close this page and we reconnect back out there. We can see that we overwrote this page to simply get our own JavaScript alert inside the HTML source code. We click OK, and we still have the filter of all of our image URLs being flipped and twisted. If we look and inspect this page code, we go up here to the top inside the head. And if we look at our script, we can see our script that specifically had it pop up an alert that says you got hacked. Again, it's a very simple JavaScript alert, but we may want it to do something else like click here to proceed or download this missing plugin, which we've done something similar to that already. We could have them click on that, grab the download file, which would just be a backdoor for us to get access to their machine. So this all kind of stems off the social engineering stuff that we talked about last week. Now, all we did was take their images here. When I first started playing with ARP spoofing and stuff, we may or may not have been doing that in a hotel, which was actually flipping all the images upside down. So we would just use HTML code to flip everybody's image upside down. We may or may not have done that here on campus too back in the day. Wouldn't recommend doing that here as well. But it's something you might do at your house. Have fun, test your kids, fire it up, do an EtherCap, ARP poison it. See if your kids notice that every picture on the website's flipped upside down.
So how do you stop that?
In this case, the issue is ARP poisoning. So the only way to truly stop ARP poisoning is to hard code MAC addresses within your switch. And that keeps them from being poisoned and the CAM table being poisoned. That's essentially what's going on here. So the virtual switch that is doing this entire network, we essentially poison that switch to say, we are this MAC address, we are that MAC address. If the switch had port security of any form whatsoever that said, no, I should only be listening to this MAC address off this port, then that would help alleviate it. The problem is if you tried to plug another computer into that port, nothing's going to happen until you match that MAC address for that port or log into the switch and fix it, one or the other. It comes back to risk assessment, right? You have to decide whether it's worth setting up port security on every single port and having to modify that every time there's a change on the network.
And what about Wi-Fi though?
Same thing, right?
Well,
To some degree.
so when you're on Wi-Fi, everybody connects to an access point.
Right.
When that access point goes off on down the thing, does it embed its MAC address in on the basically replaces its MAC address on the in the packet itself at that point?
Not at the packet itself at that point, no.
So the MAC address is still the originating MAC address. All it does is
Until it gets to the access point. It will replace the MAC address once the frame goes from wireless to wired. Yes.
right. So
But the switch has to know that I'm sending all that traffic to the AP. The AP knows a list of all of its clients.
so somebody just getting on a Wi-Fi wouldn't be able to create it on that point, correct?
They can, yes. The key to getting away from that on an ARP, on an access point, is turning on client isolation so that no two clients can ever talk together, which is a feature of most access points.
Right.
What that does is, yes, I could then ARP poison one of the other clients on the system, but I can't do anything else inside of there because I can't talk back to another client. So if I am a wireless client trying to ARP poison everybody and send all their wireless traffic back through me, that won't end up working that
So
way.
if you're doing that like on a client like that, they don't have that turned on. Essentially, you're saying you're acting like you're the DNS.
In this case, you're the default router. So we poison the default router in this case so that it would send all traffic back to us that was destined for the default router. That's how we poisoned it inside of here. So target one was that we were going to target the individual PC, the victim, and then we also target the router itself, changing that MAC address in the switch so that all traffic gets sent that way from there on out.
Do they basically do like a wild card where they target one is the router?
Target one is the host that we want to infect.
Okay,
And then target two, meaning that we are going to clone the router MAC address.
Okay, so where do we go to? So we need to target two. Is that where you affect the router?
Yeah. So where all we did was ARP poison the V switch that's running behind all of this to say that we are these MAC addresses.
Right. So then at that point, you probably just do like a wild card to say any target point, any internal IP.
You would still have to infect those individual clients. So if you wanted to poison everybody in the system, then yeah, you would poison the actual router would be your end client, and that we would want to forward that upstream, whatever the other connection of the router is. Or in this case, like say it's an access point, then you would poison further upstream. So right now we poison this PF sense. We would want to poison the outside interface of this PF sense.
Well, I meant like any, like OpenSUSE is the internal.
Right.
I wanted to spoof every one of the internals.
You would have to target every single one of them in the MAC address table.
Okay, so they don't do like.
You can't do a wild card because you don't know what MAC address to poison.
Oh, you said you can't do it by IP address at that point.
No, everything here is done by ARP layer 2. Yep. So what you would do is you could come in with, say, your Nmap scan on Kali. You could scan the network. By pinging all of those, they're going to return the MAC address. Therefore, you could now have a list of hosts on the network, which is essentially what EtherCap was doing here. When we scanned for all the available hosts, that's what it's doing. It did a ping sweep, grabbed back their MAC addresses, and then gave us a host list that we could start poisoning, which is what we see here on the screen.
So, I mean, is there like a way to where you can select them all the quickly?
You can group them together, yeah. So you can hit Control A, add that as target one, and now those are added to group one, and then you could go ahead and go there on out. Yep, yep. If you'll remember, like when we started it up here at the top, if it'll scroll back. When it came to groups, like you added those hosts in there, but we have group one, which is this, group two is going here. You would just add multiple targets to that first group and poison all those targets to make them think that to get to this IP, they need to get to this MAC address. Which there again, if we look at the Kali box, we can see that our MAC address by default here ends in D596. And you can see where these are going. So if we go out to OpenSUSE and we look at our
Like a hotel or something like that, that would just be so.
make sure I get the right one here. ARP-A. So we can see on this one, if we want to get to 254, notice how the MAC address it has in its ARP table on this host is D596. We look at our Kali Linux box, that's actually our Kali Linux box. So we poisoned the MAC address table on the OpenSUSE system and said we are that 192.168.0.254, even though we're not, but send us all that traffic. So in this case, we poisoned the actual host's ARP table in order to tell it what we were.
Why is there not something said in the protocol credentials that if that machine has an IP address, why would accept a request for the same address from another vendor saying, okay, now change this and change your ARP table?
The idea being that you could potentially move across, yes. So, but the problem is this is at the host level. So we didn't even induce so much into the switch as we did poison the actual OpenSUSE host and said we overwrote the ARP table. We put a injection in there. Notice how this IP address goes to this MAC address, which is the same as this IP address and this MAC address. So now we're saying that these two IP addresses translate to this MAC address, which is the same between the two. And by default, the host just says, okay. But if we had some kind of security on the host, then it would say something's fishy. We shouldn't have two different IP addresses with the same MAC.
Right.
But you could, right? So in what instance would that happen?
If you had, what instance would that happen?
Where would you have two IP addresses with the same MAC address in a host?
The only thing I could think would be like doing DFS or mirroring or something. Yeah, distributed file or something like that. Or DFX possibly.
Or just DHCP? Say we didn't get our lease back on 192.168.0.2. We pulled another address in there, and therefore now that new address is corresponding to a new ARP table. So we keep our entries inside of there. So there's a couple things that you can do. You can specify the length of time that your ARP entry table should be valid for. So you could increase that time so that you can't overwrite it, or you could make it really, really short. Because right now on the network, even 192.168.0.254 or the outside interface of this PF sense box thinks that it should be getting traffic back, and it's not. So it should be hammering the switch saying, why am I not getting my traffic? And if we actually Wireshark that here, we would be seeing that type of traffic. I don't remember if I got Wireshark on here or not.
To me, it just seems like such a big vulnerability in the actual protocol. So.
Well, the problem is ARP is just a helper, right? I mean, the whole goal of ARP is that we are listening to traffic and saying who's who at what. But right now, if you look at this, my computer is flooding out the network traffic, constantly advertising itself as .30 as well as 254. So that's the problem, is I'm constantly flooding the network saying it's me, it's me, it's me. Because the moment another device on the network says I am actually 192.168.0.254, everybody's host table clears. But if I'm constantly sending this traffic out, which appears to be about every 10 seconds, I'm flooding the network, telling everybody I am these two IP addresses. So if I go back to OpenSUSE.
So would OpenSUSE be flooded out also then?
It's sending its updates, but it only does it when it's requested upon it. It's not advertising it is 192.168.0.30, I believe it is.
Okay.
It's not advertising that until somebody requests it. But if I'm constantly flooding the network with response messages saying I am that number, that would be the problem. Even here, we're getting DNS requests going back, and we're saying that we're not able to get to those records. And the reason that's failing like that is it has no place to go to get that traffic. So ignore this DNS traffic. But essentially every 10 seconds, we're flooding the network with a bunch of ARPs, which there again, if we were having a firewall or an intrusion detection device, if we're noticing that something is constantly blasting out ARP, then we know we have a problem. It shouldn't be constantly blasting out ARP, especially when there's no who is out there asking for it. Matter of fact, I can try this. Can't guarantee it'll work. But we also have ARP on Kali, right? And we can look at this ARP table and we know the real ARP entries. So the real entry for .30 is DE74 and the real entry for 254 is 4768. That is the true addresses that we're sending out. That's ARP on Kali. If we look at ARP on SUS, right, it's flooded with the same IP address for no matter what IP address is on the network. In this case, just those two, because those are the only hosts we had. But if we had flooded it earlier, then Kali would constantly be sending it out for all IP addresses on the network. I am 192.168.0.10. I am 20. I am 30.
Basically, SUS is not running DNS, so PFSense is running DNS.
Mm-hmm.
Okay, so you have,
So we can see those two MAC addresses are the same.
okay, I'm following now. So basically, you poisoned the DNS server to emulate .30. That's you're the client.
Not the DNS server, even though it is the DNS server. I just poisoned the default gateway, which is I poisoned both of these devices, OpenSUSE and PFSense.
Right.
So if I go to PFSense and actually get a command prompt, let's see, shell 8. I look at ARP entries on here. I can see that. Notice .2 is going to D596. I can see .30 is also D596 and passing that traffic inside of there. So I poisoned not only OpenSUSE in its ARP table here, but I've also poisoned PFSense's ARP table as well.
Right, so you get two-way traffic.
So I can get both ways of the traffic. So now everybody's sending everything over here to the Kali Linux box. Kali knows the right one so that it knows where to forward the right traffic to. So to appear a man in the middle.
So there's nothing in there on like the DNS server that basically, because that's kind of control DNS or the gateway itself. There's nothing.
It's just controlling it at the lowest level.
So on the PFSense, there's no thing in there saying, hey, there's no way for them to block that man in the middle type attack, and send that out the bad request, the poison request,
It would have to lock down these MAC addresses in here
just on the switch only.
on the router or the switch. You would want both of them to have MAC addresses.
Okay.
So in this case, the one way to get around all this is, yes, you're doing DHCP, but do MAC reservations is one way to do it. And you static those in the ARP entry tables of your switches.
Okay. Now what happens when you're saying you're doing the static? The only question I have on that is, I know when you get the IP complex, what happens if you emulate the IP address and the MAC address on the machine? How does it know, and the switch know which way? Okay, here I've got basically two identical records. How do I know which way to go that way?
Because there's ones that are hard static in there versus ones that learned. Does that make sense? So you are statically assigning MAC addresses to IP addresses in the router or the switch in the CAM table, so that a dynamic one that it learns does not override that manual entry.
Okay.
Setting a higher priority. It's like a routing table essentially for a router, right?
Okay. Makes sense.
Like here, if I do route on this PFSense, be easier to do it over here. we can see that the default gateway is going out here, just a normal routing table, right? But if I set this metric to 0 and I static it, it cannot be overwritten by a dynamic one that it learns. And it'll always go for the one with the.
How does it know that one's dynamic versus static? Is there
In this case, it's a wild card, right? Is what it has for the default gateway as to where it's sending traffic out. This looks different. You'd have to actually go look at the router in its ARP table to see the metrics, which is what we have here, right? So in this case, we set this expiration on this ARP is going, looks like almost 1200 seconds, which is what, 20 minutes? Something like that. My math is right. But notice we have permanent addresses like what you see on that bottom one, because that's the local assigned MAC address to that local assigned IP address. We would have to set that permanently on the PF sense, which to do that, you would come in here. You could look at your.
You know what happens if it comes across the same thing? Somebody plugs a new machine in there with the same IP, because you would authenticate. That happens if you get there's IP conflict.
Right.
What does it do? Does the table look and send it to the oldest one at that point and say, well,
it would set it to the one that if it has a MAC on it or a manual assigned one with the higher metric.
what they're both, made. Okay. But how does it know which one? Because like, I'll just use it for instance, like, let's say you put something on the network, it's got, 1.1, okay?
Right.
You all of a sudden throw another machine on there, it's 1.1, but you didn't know that other one's on it because, ping's turned off on that, so not to respond back, and you don't have records of it. So you're on malicious system network you don't even know about. Then you get the IP conflict. How does the like the DNS server know which machine is supposed to be the correct one?
The DNS server wouldn't, the router would, and it would send out solicitations. Who has 192.168.1.1? In which case the switch is going to respond back with ARP, right? That says, I have this on such port, I have this on such port. Right.
How's it know which one? I mean, is it going to essentially send?
It's a function of ARP. It'll wipe them and then do the re-request again for both of them.
But if they keep trying to,
Then you permanently take down both. You can't route traffic at that point.
So basically, you're just knocking down that IP address only at that point.
Right.
Okay.
Right.
That's the answer to my question.
Yeah, you're flooding the CAM table at that point.
Right.
Which is what Callie's doing here. Like when we looked at it in Wireshark, it's constantly sending these ARPs out to flood it.
Right. I didn't know one overruled the other.
No, sometimes they'll go by our MAC address priority. So whoever's higher or lower or that kind of thing. But that it really depends on the switch as to how that's coming in. But just like here, you can go manually set static IP address or MAC addresses on the firewall. So if I come in here, I'd have to go find where they set up ARP. I know it's in here. Be on the DHCP side. And then inside of here, we could set up our pools and our addresses, but we could set up a MAC address, enable static ARP entries. And at static ARP is where we can start defining those inside of here as to who has what. And that way we don't have issues. So like here, DHCP static addresses, we could pull in specific ARPs that are going to get that particular MAC address. There's no foolproof way of stopping it in the network. The only way you can do it is shut it down by port. Dustin, Sam, Josh, you guys got any questions?
I have a quick question. If the victim traffic is TLS 1.2 encrypted, or is a man in the middle able to decode that traffic? Do you need a certificate?
It would still need it would have to clone a certificate, but yes, we can man in the middle attack HTTPS traffic. It's a little harder because we have to create certificates that are valid on both the client and on the server side. Because we are poisoning it at layer 2, right? With ARP poisoning, but it's
But
not as
without the cert,
you.
yeah, without the cert, you're not gonna be able to see anything, right?
Right, we would have to actually not only get the cert and generate our own cert, but we'd have to install that on the end client so that they think that that traffic is valid. Does that make sense? We would have to install a fake certificate on the host so that when it does its certificate lookup, it shows up as green in the browser, so to speak.
Yep. Okay.
Which we will actually do that in another lab. Let me find out what lab that is. Yeah, we'll do firewall poisoning and stuff in even Palo Alto. We'll do that as a way of doing it on purpose to inspect SSL traffic. That's what we do within the Palo Alto networks. But here, in this one, we talk about, where's the certificate? Give me a second. Right. We will do it in lab 17. So it's actually week 11 that we go through and install our own SSL certificates and doing a man in the middle attack, but with SSL.
Right. So essentially you're taking the firewall, turning it to a man in the middle on purpose.
In the Palo Alto course. And here we're doing it where we're actually just intercepting SSL traffic.
I've got so firewall.
Right.
You got the same thing.
Yep. You have to do, in order to inspect SSL traffic, you have to set up each client with a known certificate so that it actually sends that traffic on through.
Yeah, so essentially you're putting your certificate on the firewall.
Right.
Then you match that certificate on each client machine. So the client basically just on the firewall. The firewall is basically using its certificate to go out to the actual
Yes.
device on the internet.
It has to download the certificate from whatever vendor.
Right.
Yep. So it goes out to Google, pulls Google certificate, puts it on the firewall. You create your own so that you have it trusted between the client and the firewall. It takes the traffic in, decrypts it, re-encrypts it with the next certificate, and sends it out. Yep.
That's the only way to scan it. So that's exactly how I thought.
It doesn't work all the time, but it works for the most part. Like I said, Palo Alto, if you guys take 686, we do it on that. But as far as doing it from the host in terms of a vulnerability or an attack, we do that in week 11. So what that would mean is like we install an SSL certificate on a host. In other words, we get a backdoor, we transfer an SSL certificate to the host, then we perform a man in the middle attack, making that client think that they have the right SSL certificate, which is kind of like what Sam was talking about. We do that here in lab 17. Let's see, Josh, Dustin, you guys have any questions? Good question, Sam.
No.
All right, I'm gonna go ahead and stop this recording.